On the Iowa State University campus near Hamilton Hall rests a boulder that holds an inscribed plaque. The plaque reads, "On this site between 1942 and 1946, over 2 million pounds of uranium metal were produced for the Manhattan District Project by Dr. F.H. Spedding and Associates." What Spedding and his associates accomplished played an instrumental role in the dawning of the nuclear age and the development of a major federal government research laboratory, the Ames Laboratory, on the Iowa State campus. The history of the Ames Laboratory really began when Frank Spedding joined the faculty at Iowa State College. Spedding was already a nationally known rare earth chemist at the time, but the road to Ames, Iowa had been a long one. In 1929, at the age of 27, Spedding received his Ph.D. in chemistry from the University of California at Berkeley. Faced upon graduation with a poor job market for chemists due to the Great Depression, Spedding spent the next several years on temporary fellowships, one of which took him to Europe, where he lectured in France and other countries, and became acquainted with many noted chemists and physicists. In 1935, he returned to the United States and joined Cornell University on yet another fellowship. While there, his reputation as a spectroscopist and rare earth chemist grew. In 1937, he was offered an assistant professor position at Iowa State College. Not wanting yet another temporary fellowship, Spedding held out for something more permanent. His strategy paid off. A week after his first job offer at Iowa State, he received another, which he took. This one was as associate professor of chemistry and head of the physical chemistry section of the chemistry department. Spedding might have been content to teach and do research at Iowa State, but that was not to be his fate. In 1942, he was thrust into the national spotlight when he was invited by Nobel Prize-winning physicist Arthur Compton to join the metallurgical project at the University of Chicago. This top-secret government project was focused on producing a chain reaction in natural uranium, a concept that ultimately would lead to the creation of the atom bomb. Many years prior to the actual chain reaction experiment in the United States, European physicists such as Irene and Frédéric Joliot-Curie worked on experiments to split the nucleus of the atom into two distinct parts by bombarding it with neutrons. Physicist Lisa Meitner interpreted this phenomenon as fission. In 1938, physicists observed fission in the heaviest natural known element, uranium. When fission occurs, it causes the release of large amounts of energy. During a 1985 panel discussion at Iowa State, Adolf Voigt, who was a radiochemist in what became known as the Ames Project, summarized the magnitude of the energy released during fission.
The energy release was tremendous, 50 times that of a usual nuclear reaction, or about 40 million times that of a chemical reaction. More neutrons caused the reaction, but more neutrons were given off than were taken in, thereby making it very feasible that a nuclear chain reaction was possible.
The discovery of fission sparked great excitement in the scientific community because of its potential for use in the power generation and medical fields. But it was excitement tinged with concern that accompanied the realization that the enormous energy released in a fission chain reaction could not only be used for good, but also harm. If fission could be sustained in an ongoing chain reaction, the resulting energy release would allow scientists to potentially create powerful bombs with destructive power on the order of several hundred tons of TNT. Adding to the concern about fission's potential role in the development of bombs was the fear of its misuse by evil forces like Adolf Hitler. And since fission had been discovered in Germany, scientists feared the Nazis might be the first to use it to develop an atom bomb. Despite these concerns, the United States waited until 1939 to actually get involved in proving the concept of a self-sustaining chain reaction in uranium. And then only after Albert Einstein signed a letter to President Franklin Roosevelt warning of the potential for fission to be used to create bombs. The letter was presented to the president in September 1939, about 6 weeks after Hitler invaded Poland, the official start of World War II. Soon thereafter, Roosevelt formed the Uranium Committee, but despite having his support, progress to prove the self-sustaining chain reaction was slow. Events changed dramatically on December 7, 1941, when the Japanese bombed Pearl Harbor. 3 days later, Germany and Italy declared war on the United States. This added increased urgency to proving that a self-sustaining chain reaction in uranium was possible. The Uranium Committee quickly appointed 3 program chiefs at 3 different universities to oversee various aspects of atomic energy research. Arthur Compton was given responsibility for building the nuclear reactor, or pile, at the University of Chicago, where the chain reaction would take place. Compton quickly created the metallurgical laboratory at Chicago and asked Spedding to take over the new laboratory's chemistry division. Compton considered Spedding's background in rare earth chemistry a valuable asset to the project because much needed to be learned about the chemical and metallurgical qualities of uranium and its byproducts. Spedding began setting up shop at the University of Chicago, but soon made a decision that would forever affect Iowa State. Spedding later recalled that decision.
And we couldn't do it at Chicago until we built a building, until we got some staff together. And I told him that we had a metallograph and we had a furnace here at Ames, and that we could get some of this work going. So as soon as I got back to Ames, the first group I took into my program with my own graduate students. Dr. Wilhelm had been the other man doing all the physical chemistry at Ames, and I approached him. I knew his abilities pretty well, and asked him if he wouldn't join us. So that's the way we started.
In February 1942, Spedding appointed Harley Wilhelm, Associate Director of the project at Iowa State. Wilhelm was given responsibility for the metallurgy area. Soon thereafter, Spedding hired other key personnel. When his staff was in place, he asked for clearance from Iowa State President Charles Friley to officially establish the top-secret Ames Project at the college under the Manhattan Engineer District. This district within the War Department's Army Corps of Engineers was named for the location of its headquarters in New York City and was tasked with overseeing construction of the various facilities for the atom bomb project. The project later became known as the Manhattan Project.
Dr. Fowley had to take me on faith because I told him that we were going to do a very secret project and that I couldn't tell him about it, but that I'd like to get him cleared as quick as we could so I could tell him all about it, and he gave us complete cooperation.
Friley released Spedding from half his duties at Iowa State. This allowed him to work part-time in Chicago, organizing the chemistry division at the metallurgical laboratory, and part-time in Ames, working to solve chemical problems. Wilhelm remembered how Spedding's schedule was split to accommodate time in both Ames and Chicago.
So Spedding, about the middle of December, started working with Compton, and he would go into Chicago on Sunday night on the train, and then come back on the city of Denver on Friday evening, leave Chicago at 5 o'clock, be in Ames at 10 o'clock, and be here Saturday and most of Sunday, and back to Chicago again. Then after Compton decided to put us on duty here in the metallurgy group, then when Spedding would come back Friday night, Saturday morning, he'd meet with us and tell us what was going on at Chicago, and we'd tell him what we had done here during a week while he's gone.
Efforts to conduct the fission chain reaction experiment hinged upon the availability of pure uranium metal. Purity was essential because scientists believe impurities would absorb the neutrons that were key to starting a self-sustaining reaction. Uranium generally came in the form of oxide, and although at the time there were quantities of uranium oxide available in the United States and Canada, the supply was impure. The best place to get uranium oxide was in Belgian Congo, but the Nazis occupied Belgium and had stopped that country's shipments of oxide from the Congo to other countries. There were industry processes available at the time to produce pure uranium metal, but only in gram quantities, and the chain reaction experiment would need tons of pure uranium to be successful. The Ames Project had a twofold challenge. First, to develop a method for producing large quantities of highly pure uranium metal in a short time. And second, to develop a procedure for large-scale casting of the metal. For many months, the Ames scientists experimented with different ways of producing high-quality uranium metal using a thermite reaction, but all efforts failed. Their luck changed, however, in early August 1942 when Spedding instructed them to do a bomb reduction experiment with calcium and uranium tetrafluoride. C.F. Gray, a metal caster for the Ames Project, commented on what Wilhelm did next.
And so they made a little bomb in the shop and mixed up some ground calcium, as I recall. And he triggered this thermite bomb with electric coil and some magnesium. And it was real interesting. You know, he set it out in that little patio there on the west side of the chemistry building, the same level as the basement, and everybody was peeking over the edge of the window to see what was going to happen. And they threw the switch, and a little smoke came out. And when the bomb cooled down, they cooled it. They had accomplished one thing. They had reduced the uranium.
The next challenge was to get the pulverized calcium to melt and react with the uranium tetrafluoride. So the materials were placed in a crucible and heated to 600 degrees Celsius. The resulting reaction produced molten calcium fluoride and uranium metal. The uranium metal, being denser, sank to the bottom of the bomb and formed a button or biscuit of material. Wilhelm commented on the simple process.
Well, the first one, we only got a couple of ounces, first reaction. All you had to do was ignite it, a mixture, and it'll heat itself up and melt all the products, and the uranium was heavier than the calcium fluoride that was formed, and so the uranium would go to the bottom of the chamber, the calcium fluoride on top. Let it cool, turn it upside down, and bounce it, and the metal comes out. See, separated.
After several modifications to the reduction process, several biscuits with approximately 90% purity were produced. These were cast into a final 11-pound ingot of pure metallic uranium. On September 24, 1942, Wilhelm hand-carried this ingot by train to Spedding at the University of Chicago. Together, they showed it to Arthur Compton, who, as Wilhelm later recalled, had trouble believing what he was seeing.
Compton's eyes bugged out when he saw a piece like that, one 11-pound piece. He'd paid $10,000 for a 2-pound piece.
But Compton would not be so easily convinced he was looking at a solid ingot of uranium. He said, "I bet there's a pipe or hole inside." To prove there wasn't, Wilhelm took the ingot to a nearby shop where he had a worker cut it open. The cutting revealed no hole. Within a week, Richard Doan, the director of the metallurgical laboratory, traveled to Iowa State to write a $30,000 contract for the Ames Project to begin producing 100 pounds of uranium per week. Under the new arrangement, the Ames Project scientists would continue producing uranium metal until they could show large companies like DuPont how to incorporate the Ames process into their own plants. To do this, the scientists needed more space for people and equipment. Up to this point, the reduction work had been performed in the chemistry building, but Spedding and Wilhelm soon found a new site that suited their expansion plans. It was an old, temporary wooden building on the east side of the Iowa State campus that, at the time, was being used primarily as a combination garage and popcorn laboratory. Iowa State quickly signed the building over to the project. Next, the scientists needed a full-scale machine shop. Fortunately, Wilhelm found an entire shop for sale in Ames. The shop and its tools were purchased, lock, stock, and barrel, and moved to the old building. The shop's owner was hired to work in the new plant, which was officially named the Physical Chemistry Annex, but was quickly nicknamed Little Ankeny after a war munitions plant in Ankeny, Iowa. As efforts continued to get the pilot plant in Ames up and operating, Italian Nobel laureate Enrico Fermi began building the pile, or reactor, for the self-sustaining chain reaction experiment at the University of Chicago. The site for the pile was in a room in the squash court under the west stands of Stagg Field, a little-used football stadium. The pile was quite large, 26 feet in diameter. It consisted of 15 layers of graphite bricks with machined holes in them. These holes would hold approximately 22,000 slugs of uranium and uranium oxide. The ingots, or eggs of uranium, sent from Ames to Chicago, were cast as small solid cylinders. These eggs would be used to help the pile reach critical size, or the point at which it would be able to sustain a nuclear chain reaction. Spedding commented on the magnitude of the Ames Project's efforts to supply uranium to Chicago for the chain reaction experiment.
In the last month before the reactor went critical at Chicago, we managed to supply them with 2 tons of metal, which was a third of the total amount of metal they were able to get to that time.
On December 2, 1942, Fermi determined the pile had reached critical size, and the chain reaction experiment was ready to proceed. Fermi directed the experiment while the other scientists watched. Compton later described the chain reaction event.
On the balcony, a dozen scientists were watching the instruments and handling the controls. Across the room was a large cubical pile of graphite and uranium blocks in which we hoped the atomic chain reaction would develop. The Geiger counters registering the neutrons from the reactor began to click faster and faster till their sound became a rattle. Throw in the safety rods, came Fermi's order, and you could see the pointer move right back to zero. For the first time, atomic power had been released. It had been controlled and stopped.
The Chicago pile operated for 28 minutes and produced 1/2 watt of power. Spedding, in his capacity as head of the chemistry section for the Chicago-Manhattan Project, was one of the witnesses to this historic event. Following the success of the chain reaction experiment, more uranium was needed to create a larger reactor at the Clinton Engineer Works in Oak Ridge, Tennessee. The Ames group kept churning out uranium, eventually producing 90% of the uranium that went into the Clinton reactor. With new equipment in place in Little Ankeny, uranium production was stepped up, rising from an average of 3,600 pounds a week in early January 1943 to nearly 36,000 pounds a week 6 months later. At the time production of uranium was underway in the chemistry building and later in Little Ankeny, the focus was on doing whatever was necessary to produce pure uranium, first for the chain reaction experiment and then later the overall war effort. Spedding described in life and death terms the importance of efforts to speed production of uranium.
But during the war, the main job was to get it done and not how you did it, because the pressure was there that if it could be made to work, it could shorten the war and save a great many lives.
Safety was never deliberately compromised as a result of the drive to produce uranium in Ames. However, the unknown health factors associated with beryllium, one of the materials to which workers were exposed during the production process, ultimately led to health problems and even loss of life. Beryllium exposure occurred at government plants around the country associated with the Manhattan Project. The workers' sacrifices, however, have not been ignored by the government, which in 1998 implemented a program to provide the former workers stricken with berylliosis free health care. In 2000, the government added a program to provide financial compensation for the workers or their survivors. Almost as quickly as it began, the Ames Project began to wind down. As expected, industrial plants began to take over the process developed at Iowa State. This caused the Ames Project to begin to reduce its output of uranium. But this did not bring an end to the Ames scientists' work. They developed a successful method to recover uranium from scrap metal machine turnings from Ames and other places. The Ames Project recovered and shipped over 600,000 pounds of scrap uranium using this reduction method. By December 1945, this process was also taken over by industry. Iowa State discontinued most uranium operations in August 1945, coinciding with the end of World War II. Following uranium production, Little Ankeny was used for a time to produce thorium metal, but eventually this work ended, and in 1953 the building was torn down. For its dedication to the war effort, Iowa State received the Army-Navy E flag with 4 stars, signifying more than 2 years of excellence in the production of metallic uranium as a vital war material. The flag was presented on October 12, 1945, to Iowa State President Charles Friley by Major General Leslie Groves, commander of the Manhattan Project, and it flew for 2 to 3 years on the flagpole on Central Campus. Iowa State became the only college ever to receive the Army-Navy E flag. Spedding recounted his feelings on the awarding of the flag.
And I must say that I got quite a bit of pride, personal pride out of this. I think Dr. Wilhelm did too. And we were in competition with industry during this period. We were professors, and our process won out over all others. And we got the Army and Navy E award for it.
Perhaps an even greater tribute to Iowa State's accomplishment was the founding of the Ames Laboratory. The Atomic Energy Commission, or AEC, which coordinated government research, established Ames Laboratory on May 17, 1947. The AEC awarded the contract for the operation of the Ames Lab to Iowa State under the university's Institute for Atomic Research and appointed Spedding the laboratory's first director. Iowa State has been the sole contractor for the Ames Laboratory ever since its inception. Quite naturally, the work performed by the Ames scientists impacted their professional careers, but it also dramatically impacted their personal lives. Normally, for example, a college professor would not have been able to determine whether or not someone would be drafted. But with his newfound authority, Spedding was able to do just that for the men he needed on the project. One of those men was Ray Fisher, who was a sophomore chemistry student at Iowa State in 1942. Spedding wanted Fisher to be a chemist in the analytical section and check the purity of the uranium that was being processed. There was only one problem. Fisher had been drafted. Fisher recounted what happened next.
I'd been drafted and had gone down to Des Moines, had my physical, and was all set to go. That was after I'd been working here a while, and Dr. Spedding called me and he says, what are you doing, trying to get out of this, get away from me? And I said, no, they've drafted me. He said, well, he's going to pull me back. So I wasn't permitted to be drafted, which was a godsend to me.
Like Fisher, many of the participants in the Ames Project were young men and women, undergraduate or graduate students. Harry Sveck, a glassblower for the Ames Project, was only 24, but he didn't see age as any type of barrier. On the contrary, he felt the young scientist's inexperience actually helped expedite completion of the Ames Project research.
I think it was a blessing because we didn't know what you couldn't do. And so we did it. You know, oftentimes when you have experts telling you what can be done and what can't be done, it sort of beclouds your thinking. But we didn't have any experts. So you just went ahead and did what you think, what your thought process would generate.
Age also didn't get in the way of the young student's devotion to the Ames Project. Fisher recounted that students like him were inspired to succeed on the project in large part out of their respect for Spedding and Wilhelm, who put in countless hours on the job.
We didn't watch the clock, and we were there till we could find a convenient time to break, and we played a lot too. And when we had a few hours in the daytime, we'd play touch football and all. But it was exciting. New things were coming. We had seminars, and usually on Sunday morning, and they lasted, and in the evenings besides. And they brought us up to date, and we were. It wasn't as a need to know. We pretty well were in the know of. I'm sure Dr. Spedding knew more things about what was going on than I, but they were quite generous in letting us know, and that inspired us to know what you're doing and why you're doing it. Just to work on something and not know what it's all about wouldn't have given the dedication that I think we all had felt.
This dedication was shared by other students like Norman Carlson, who joined the Ames Project in 1943 and began analytical work on uranium. Carlson recounted that the time he spent as part of the Ames Project was one of the high points of his professional career.
This really was one of the exciting periods of my scientific professional life, to be part of this project. This was a great way for a young scientist to break into a field. I mean, this was absolutely a revolutionary discovery, this whole thing of atomic fission or nuclear energy or what have you. And to be on the ground floor, even though I obviously was a pretty low-level scientist at that stage, still to be on the ground floor of such a revolutionary advance in science has left its mark on me, I think. As I look back on my career, I think, well, you know, this was the excitement of I suppose the NASA people when they landed on the moon would be somewhat comparable to what we experienced here.
Secrecy was a top priority when it came to the Ames Project. Being in the know meant you were one of a privileged few in Ames. David Peterson, a student who worked on the uranium production crew, recalled that secrecy was something not to be taken lightly.
One of the ways of making sure that people were minding their P's and Q's with regard to security was that all of us that were of draft age were told that if we violated any of the regulations with regard to secrecy and security, that we'd be drafted and sent overseas to the front lines. And so that was a powerful motivation to be pretty careful.
But despite the best efforts, some activities associated with the Ames Project just couldn't be kept secret. For example, the armed guards who prevented the curious from getting too close to the production areas and who came in on the trains to pick up the uranium attracted a lot of attention. And so did the regular fires in Little Ankeny, fires that outside firefighters were not allowed to help put out. Spedding recalled one occurrence in Little Ankeny that literally lit up the campus.
There was a great deal of curiosity on the campus as to what we were doing, particularly as once in a while one of our retorts would blow up, and with the magnesium, which is what you use in flash powder, they would light up the whole building, and it gave a illusion. The light was so bright that the building swelled up and then sunk back. And the college press office was right across the street from this building, so naturally their curiosity was very great, but nobody would talk, so they didn't know what was going on.
Although the Ames Project work was serious, there were elements of humor associated with it. Take, for example, the problem of what to do with the scrap and slag left over from the reduction process at Little Ankeny. At first, this waste material was deposited in a pit on Iowa State property. But then the decision was made to dig up the waste material and ship it to New Jersey for disposal. But finding suitable containers in which to transport the materials remained a dilemma. Then Wayne Keller, who worked on uranium metal reduction, suggested using empty whiskey barrels, which he thought could be obtained from the Hiram Walker Distillery in his home state of Kentucky. Soon those barrels were arriving in Ames by the freight car load, and every time they did, the workers volunteered immediately to help unload them. Thinking this altruism was a bit unusual, Wilhelm investigated and soon learned why unloading whiskey barrels was such a popular job.
Well, they found very shortly that if you took the top rim off of the barrel, that the staves, or whatever it is, the side of the barrel expands, and you can lift that lid out. Now, if you turn it at a certain angle, if there's any whiskey in the charcoal at all, it'll drain down the corner. See? They leave them set in the corner ways, and then they get in there with a rubber glove and a sponge, and they can sponge it out. See? Just put it in a jug. Well, we found out why they wanted to work on the bull gang. See? And it is because these whiskey barrels were very interesting to the people that worked on the bull gang.
Any questions the public had about the Ames Project were cleared up on August 6, 1945. That's the day the United States dropped the atomic bomb on Hiroshima, Japan. A radio announcement that Iowa State had been involved in research efforts that led to the creation of the atom bomb came from the Secretary of War. Wilhelm recalled that radio broadcast.
Well, when they named Iowa State College, the whole chemistry building lit up. Everybody hollered all over the campus about Iowa State College. Of course, they didn't know what we'd been doing, but they knew then what it was we were working on.
That puffed us up a little bit. Well, it made up for a lot of the hours that we'd spent there, because those were long days, 16-hour days, and it was fun though. We were each needling the other to get it done.
Soon, word of Iowa State's involvement in the effort to end the war spread much farther than Ames. The Des Moines Register called a short time after the news came over the radio, and the newspaper did interviews for a story on Iowa State's involvement in the top-secret Manhattan Project. The story, when printed, quickly spread the news of the Iowa State scientists' accomplishments. But for many of the scientists, the adulation was secondary to the feeling of personal reward for a job well done. Norman Carlson expressed his feelings about participating in the Ames Project in the following way.
I think it's hard to realize the sense of euphoria and of actually a feeling of being heroes, I guess is the term I often have used, that we were heroes of having, just brought this war to an abrupt and instant conclusion. And I think we felt that was our big contribution.
In June 1985, 40 years after uranium production ceased at Iowa State, approximately 100 of the original group of scientists, their spouses and others, got together on alumni days at Iowa State for a Manhattan Project reception. The group toured the campus and the Ames Laboratory. Following these activities, one unidentified participant summarized the journey of the Ames Laboratory, a journey that began as one scientist's dream and culminated in the development of a federal research laboratory with an international reputation for excellence. The individual said, "Spedding would drop in where we were working and shoot the breeze, and he would say, 'Someday we're going to have a great laboratory here,' and we would laugh and say, 'Oh yeah, sure.' Well, it turned out the way he said."